Namaskar. Good morning to everyone. Myself, Dr. Bijukumar Datta, Assistant Professor, Department of Mathematics, under the School of Basic Science, the Assam Kaziranga University, Jorhat, Assam. Today, on behalf of Department of Mathematics, I welcome you all to this final day of International Webinar on Fundamental of Mathematics 2021. I find immense pleasure in introducing our today resource person, Dr. Neelam Saikia, Postdoctoral Fellow, Department of Mathematics, University of Virginia, US. Her research area in the field of number theory. She published a number of research articles in various reputed journals. Also, she worked as an inspiring faculty at Indian Institute of Technology, Guwahati. We are very grateful to Dr. Saikia for accepting our invitation and marking her presence here. I now welcome Dr. Saikia to deliver her lecture. Thank you.
Good morning, everyone. I am Neelam Saikia. Currently, I am a postdoctoral fellow at University of Virginia. I would like to thank Dr. Dimpal Mahanta and all the faculty members of the Kaziranga University for this invitation. I think today is the last day of this webinar, so I'm really very excited to be here. Today, I'll be talking about primes in arithmetic progression. This topic is quite famous in number theory. All these results that I'm going to present are very well known to everyone. So if you might have seen these results before. However, if you are viewing them for the first time, then try to think how these ideas are coming and ultimately how we have such beautiful results. So let's begin. First, we pick some basic notation. If n is a product of these two numbers, a and b, then we say that a divides n and b divides n. We use this notation a congruent to b modulo n if and only if n divides a minus b. If n divides a and n divides b, then it is easy to verify that n divides a plus b. If GCD of a and b is equal to 1, that is the greatest common divisor of a and b is 1, then we say that a is relatively prime to b or a is co-prime to b. Let's just recall one of the numbers known as the prime number. So a prime number is a number which is greater than 1 and the only divisors of this number is either 1 or the number itself. For example, these are the prime numbers which are less than 100. We now recall one of an important theorem in number theory, which is known as the fundamental theorem of arithmetic. So this states that every positive integer greater than 1 is either a prime or can be written uniquely as a product of primes. And I think we have been using this theorem since our childhood when we learn about how to factorize a number. And I think unknowingly we are using this theorem, but here we have some, we have a well-defined statement. So here are some examples. So we can write 4 as 2 square. 5 can be written as 5 because 5 cannot be factorized further. And then 6 can be written as 2 times 3, and then so on. In general, we can write n as the product of these primes, p1, p2 up to pk, with this powers, where these are all primes and in ei's are integers greater than or equal to 1. So now someone can ask you, what is the largest prime? Can you produce one largest prime? So we have a very famous theorem which states that the primes are infinite. Okay. That is, there is no largest prime. So there are many proofs available in number theory which gives that primes are infinite. However, one of an oldest proof is given by Euclid, And this proof is simple and I think it is easy to understand. So let me just give this proof. So to prove this, Euclid used the method of contradiction. So if you want to prove that that the primes are infinite, so we assume that the primes are not that primes are not infinite. That is, the set of prime numbers is finite. So let's just suppose that these numbers are p1, p2 up to pn. That is, these are the only primes we have. There is no other prime. Then we can construct this number n like this. Clearly, n is greater than 1. So by the fundamental theorem of arithmetic, n is either a prime or is a product of primes. Of course, n is not a prime since n is bigger than each of these primes, p1, p2 up to pn, and we have assumed that these are the only primes, and since n is bigger than each of these primes, so n cannot be a prime. So if n is not a prime, then by fundamental theorem of arithmetic, we can say that n is a product of primes. But but from the construction of n, we can say that there is no prime which divides n, because these are the only primes, p1, p2 up to pn. These are the only primes which can divide n. But if these are the primes divide n, that means that prime divide this product. So ultimately, we get that prime divides 1, which is a contradiction. So there is no prime which divides n, and n is not a prime. So this is a contradiction. So this proves that our assumption is wrong. That is, there is infinitely many primes. Okay, so now we are coming closer to our topic. So let me just recall what is an arithmetic progression. So if h and k are two integers, then an arithmetic progression, which first term is h and the common difference is k, is consists of all these numbers, kn plus h, where n runs over 0, 1, 2, and so on. For example, if we choose h equal to 1 and k equal to 2, then the arithmetic progression consists of these numbers 1, 3, 5, then 2n plus 1, and so on. And we can say that this consists of all the odd numbers, because any odd number can be written as some 2m plus 1, and which falls somewhere in this progression. And we know that the primes are odd except the 2, right? The only even prime is 2, except 2. All other primes are odd, right? And we can see here that these 3 and 5, these are all lying in this arithmetic progression. And since we know that a prime apart from 2 is an odd number, so we can say that this arithmetic progression contains infinitely many primes. In fact, all the primes except 2. So if the common factor between h and k is d, which is greater than 1, then we can say that d divides all these numbers kn plus h. That is, if h and k has a common factor greater than 1, then that factor divides all the numbers in this arithmetic progression. So this implies that if the common factor of h and d, or we can say that if the GCD of h and k is greater than 1, then this arithmetic progression doesn't contain infinitely many primes. But here we can say that if the GCD of h and k is 1, then it may contain infinitely many primes. For example, this arithmetic progression contains infinitely many primes. But if the GCD is greater than 1, then there is no chance that this arithmetic progression contains infinitely many primes. So what is the criteria? That how can we say that an arithmetic progression contain infinitely many primes. Of course, one case we have to rule out that if the GCD is greater than 1, then of course that arithmetic progression doesn't contain infinitely many primes. However, if the GCD is GCD of H and K is 1, then whether this arithmetic progression contain infinitely many primes is a problem of study, right? So so here we consider this question. So that it is natural to consider the question. What can we say about the same if GCD of H and K equal to 1? That is, whenever the GCD of H and K equal to 1, whether this arithmetic progression contain infinitely many primes. So already we have one example here for the odd integer case. So here I'll give some more examples. So for the first example, we consider this numbers of this form 4n minus 1. So here we have h as minus 1 and k as 4. So of course the GCD of this and this is 1. So here we prove that there are infinitely many primes of the form 4n minus 1. So the proof is very simple. So again, here we use the method of contradiction. So first assume that there are only finitely many numbers which are prime and which has this form. And let p be the largest among all of them. Then we consider this integer n, which is the product of 4, 3, 5 up to p minus 1. But this product contains all the odd primes which are less than or equal to p. Now we know that the form of n is of this sum. This sum is of the form 4n minus 1. So since this is a number which of the form 4n minus 1, so it cannot be a prime, because here from the construction we can see that n is greater than p, right? And p is the largest prime of the form 4n minus 1, and n is definitely bigger than p. So n cannot be a prime. So if n is not a prime, then by the fundamental theorem of arithmetic, we can say that n is a product of primes. And we can say that there is no prime which is less than p and which divides n. Because in this product, all the primes which are less than or equal to p appear here, right? So if n has a prime factor, then those prime factor must be greater than p. All right. So since that prime factor, say for example q, so if q is a prime factor of n, then q must be greater than p. And since p is the largest prime which contains, which is of the form 4n minus 1, so this factor of n, which is q, must be of the form 4n plus 1, because it has no other option, because since q is a prime, so it is either 4n plus 1 or 4n minus 1. 4n minus 1 option we have to omit, because that prime factor q is greater than p. So we can say that prime factor of n, which is q, is of the form 4n plus 1. In fact, we can say that all the prime factors of n are of the form 4n plus 1. If all the prime factors of n are of the form 4n plus 1, then ultimately the product would be of the form 4n plus 1. But here we have n is of the form 4n minus 1. How it will be possible, right? So n must have a prime factor of the form 4n minus 1, which is a contradiction, right? So we can say that there are infinitely many primes of the form 4n minus 1. Similarly, we can show that there are infinitely many primes of the form 4n plus 1. So now what about a general case? Like we have given 3 examples: odd numbers, then 4n plus 1, 4n minus 1. Now what about the general case? So this was studied by Dirichlet. So he gives a necessary and sufficient condition for infinitely many primes. Necessary condition is that an arithmetic progression which contains infinitely many primes, then the GCD should be 1. GCD of H and K should be 1. And Dirichlet proved that this is the sufficient condition for which the arithmetic progression contains infinitely many primes. So this is his theorem. It states that if GCD of H and K is 1, then the arithmetic progression contains infinitely many primes. That is, there are infinitely many primes of the form nk plus h. So now to prove Dirichlet theorem, so it is enough to show that if we consider this weighted sums of reciprocals of 1 by p, which is weighted by log p, and if we consider this this partial sum where these primes are congruent to h modulo k, then this sum can be averaged by this. Or else we can say that this sum is equal to 1 upon p of k times log of x plus big O of 1, where this function phi and big O of 1. So we will discuss what are these objects, we'll see later. But for the time being, we say that these are some bounded functions, p of k and big O of 1. So these are some bounded functions. So if we can show that this sum is equal to this, so note that, so on the right hand side, so this is the main term, right? Log of x. And we can say that if x goes to infinity, then log of x also goes to infinity, right? That means if x goes to infinity, the right hand side of this expression goes to infinity. Since these two expressions are same, so this sum is also going to infinity. And if this is going to infinity, that means this sum contains infinitely many primes of the form h plus nk, right? That is, in this arithmetic progression, we have infinitely many primes. If it has finitely many primes, then this sum would be finite. Then left hand side would be a bounded function, whereas right hand side would be an unbounded function, which is a contradiction. So this would be infinite. That means that this sum contains infinitely many primes. So now to prove Dirichlet's theorem, that is, if you want to prove this identity, so let's just recall some functions, notations, some theory that are going to use to prove this identity. So please bear with me. So first we define arithmetic functions. So an arithmetic function is a real or complex valued function which is defined on the set of positive integers. For example, we can consider the Mobius function, which is denoted by mu. So this function mu is defined like this. So mu of n is equal to 1 if n is equal to 1. So mu of n is equal to minus 1 to the k if n is the product of these distinct primes, p1, p2 up to pk, where all these primes are distinct. And if n contains a square factor, then it will be 0. Right. And this function is quite useful in number theory. Next function we would like to consider is the very famous theorem, a very famous function, which is the Euler's torsion function. So this function is defined as so phi of n is the positive integers, is the number of positive integers not exceeding n and which are relatively prime to n. That is, phi of n counts all the positive integers lying between 1 and n which are co-prime to n, right? For example, we can say that phi of 2 is equal to 1 because 1 is the only number which is co-prime to 2. So phi of 2 is 1. Phi of 4 is 2 because 1 and 3 are the two numbers lying between 1 and 4 which are co-prime to 4. Similarly, phi of 5 is 4 because 1, 2, 3, 4, these are the four numbers which are co-prime to 5 and which are also less than or equal to 5. In general, we can say that if p is a prime, then phi of p is p minus 1. And it is very easy to verify because also all the numbers lying between 1 to p minus 1, so all are co-prime to p, right? And these are only numbers. There is no other numbers. So p of p equal to p minus 1. Next, we are going to define is mango function. So for every positive integer n greater than or equal to 1, we define this function like this. So if n is power of some prime, then this mango function, which is defined by this lambda, so this lambda of n is equal to log of n if n is power of some prime. Otherwise, this function would be 0. So now we introduce one product which is known as the Dirichlet product. This product is very useful in the theory of arithmetic functions because this product is used to produce more arithmetic functions. So for example, we can say that if f and g are two arithmetical functions, then their Dirichlet product, or maybe you can say Dirichlet convolution, is the arithmetical function h, which is written like this, f asterisk g. So this function at n defined as the sum f of d times g of n by d, where the sum runs over all the positive divisors of n. Right? So now we introduce another convolution, which is known as the generalized convolution. So if f is a real or complex valued function, which is defined on the positive real axis, such that f of x equal to 0 if x lying in this interval, and if alpha is an arithmetic function, then the function defined by this alpha circle f at x, this function is defined like this as the Purcell sum. So evaluated at alpha of n times f of x by n. So this sum is known as the generalized convolution of alpha and f. And of course, this function also vanishes in this interval 0 to 1 because it follows from the definition of this function, right? In fact, if fx is 0 for all non-integral x, then the restriction of f to the integers is an arithmetic function. And then this generalized convolution, so this becomes the Dirichlet product. I think it is easy to verify. So now we'll recall one property which is basically considered as some associativity. So if alpha and beta are two arithmetical functions, then we have this identity. So if we consider beta with f, and then we compute the function, and then after that we'll compute this, which is equal to if we compute this, and then we compute with this. The proof is very simple. So here we assume that x is greater than 1, x is greater than 0. Okay. So if we consider the left hand side here, so here first what we do, so where we first apply this this one. So we have from the definition alpha of n, and whatever we left here, we can write as b circle f x by n. Then we again apply the definition here. So we can write like this. Okay. So now we can write this sum as this, where here this numbers n and m are varying such that the product mn is less than or equal to x. So now if we choose this m and n as k, then here we have k less than or equal to x. And here k is what? K is product of n and m. So here we have, in terms of k, we can write this sum. So ultimately this will behave like this Dirichlet product, right? So ultimately when we like a little bit of manipulation, we obtain this. So we have that this would be equal to this for all of x. So you can say that these two are equal. Next, we see some versus sums of a Dirichlet product. So if h is the Dirichlet product of these two arithmetical function f and g, then let this h as partial sum, this capital F as this partial sum, and this g as this partial sum, where the sums are runs over all the integers which are less than or equal to x. If we have this, then we have this. That h can be written in terms of this. So this is some kind of generalized convolution that we have mentioned in our previous slide. So the proof is very simple. Here we produce one arithmetical function, or maybe not as arithmetical function, because here we have all these numbers. So let's just define this function on the positive real axis as 0 when x lies in this interval and 1 otherwise. So it is easy to verify that f is equal to this and g equal to this. So we have this. So I think first identity is here because we have f composed with this g, and we replace g by this, and since f and g are arithmetical functions, so by associativity we have here, we can have this Dirichlet product, and so this is h, so h of this. Similarly, we have this. So what is the point of using all this notation? So here, using these functions, we have some very nice identities. For example, if we consider g of n as 1 for all n, and g of x as this floor function x, where this floor function is defined as the greatest integer less than or equal to x. That is, if x is supports 10, then g of 10 would be 10. If x is 10.5, g of x would be 10. So that means this is the greatest integer less than or equal to x. So if we use these two functions here, we obtain this identity. That means if f is any arithmetical function, then we have this double sum becomes this single sum. So this is clearly viewed from this previous identity here. Here gx is 1, g of n is 1, right? And this would be capital. I mean, capital of g would be floor of x. So from here, we have this identity. In particular, if we choose f as this Mengel function, which is denoted by this lambda, then from this identity, we obtain this corollary. So here we have f as this Mengel function. So from the middle one, we have this, then this, and then since this lambda of d divides n, so this is log of n. This is follows from the definition. because log this lambda of d is log of p if d equal to some prime power, otherwise 0. So here this sum runs over all the prime power factors of n. So basically, after viewing this carefully, we obtain that this sum would be equal to log of n. So I mean here we have the sum of log of n, where n is less than or equal to x. That is, this sum can be written as log of 1, which is 0, and log of 2 plus log of 3 up to the integer, which is less than or equal to this floor of x. And since log of a plus b equal to log of ab, so using that property, we can say that this sum is equal to log of floor of x factorial. So now we introduce one more function, one more formula, which is known as the generalized Mobius inversion. So if f is a completely multiplicative function, that is, if alpha of mn is equal to alpha of n into alpha of m, then we have, then for this function, which is written in this form, we can have this f of x, where this mu, so this is the Mobius function, and alpha is our, sorry, just a minute. And this this mu is our Mobius function and alpha is. So this is known as the generalized Mobius inversion formula. So now we introduce some notation, which is known as the big O notation. This notation is used when we want to study asymptotic equality of functions, that is, when two functions are equal as their asymptotic. So if g of x is a positive function for all x greater than or equal to a, then we write f of x as big O of g of x, if and only if there exists some constant m greater than 0, such that this norm of f of x is less than or equal to m times gx. That is, f of x is absolutely bounded by m times g of x. Then we write f of x as big O of gx. So here it is important to note that if f of t is the big O of g of t for all t greater than or equal to a, then this implies that in this integration, if we consider this integration of f of t, then this can be written in terms of big O of this integration. That means big O and this integration, thus this is commutative. It is easy to verify. So now we see some average of arithmetic numbers, and it is quite useful in number theory when you study distribution kind of problem. You study some averaging of some arithmetic functions. So these are very useful in number theory. So if we consider x is greater than or equal to 2, then the following are true. So here we have our first asymptotic formula. If we consider this partial sum of this floor function, where it is weighted by this lambda function, then we obtain that this sum is equal to log of floor of x factorial. And I think this is earlier we have seen how this occur, and then we have that this would be asymptotically equal to this identity. And similarly, in the second case, so we have that, so these two are same. So here, what we can notice that here we can estimate this part by x, because log of x is less than x. So we combine these two as big O of x. So yeah, so this is trivial. So next identity is, so if you consider this log p and then this x of p, x by p of this floor function, then this is equal to this expression. So here we are not going to prove all these identities because the proofs are more or less similar. So in fact, we will prove the first identity here. So let me just go back to this, just a moment. Yeah, here it is. So we'll prove this this formula. So this is not very straightforward. We are going to use one of a famous summation formula of Euler, which states that if f has a continuous derivative f prime on some interval, then this sum, where the sum over all the integers lying between y and x, then this sum can be replaced by these two integrals with these two extra terms. So the proof of this identity is very well known. You can see the proof in any standard book of number theory. So I leave this as an exercise. Okay. So we're going to use this sum to prove this identity. So here we first laid that f of t is equal to log of t. So we can see that what is the f prime of t? So f prime of t will be 1 over t. So this is so 1 over t is continuous for t greater than 0. So here we use the interval as 1 to x. So here we choose y as 1. So in this 1 to x, the 1 over t is continuous. So yeah, we can use it. So yeah, here we can replace f of t by this log of n. And if we put on the right side, if we put on the integral, we have this. So this is just direct substitution, where for this one we have 0, because here y is, we have chosen as 1, so this would be 0. So we left with only these 3 terms here. So yeah, from the first integral, what we have, so here we simply apply the integral by parts, and we obtain that this is equal to x log of x minus x plus 1. So this is trivial. Whereas the second identity will compute in a bit, where the third identity, what we have here is, so this x minus log of x. So this x minus, not log of x, sorry, x minus this floor of x. So this term is, so this is lying between 0 and 1, strictly. I mean, this is lying between 0 less than equal to this term, or less than equal to less than 1, not exactly 1. So this is a small quantity. So we can average this by log of x. That's what we have written, because this is small. It's not going to infinite when x goes to infinite, because this is always lying between 0 and 1, right? So we can average this by big O of log of x. So now see that. So now we consider this integral here. So here we can see that since this is lying between 0 and 1, so this function can be written as big O of 1 over t. So if this is big O of 1 over t, so then it is clear that this integral would be big O of this integral. And this integral is nothing but big O of log of x. So if we put all the things here, so we obtain this identity like this, and we absorb 1 here. So we are done. So now next, again, go back to the slides where we are. Yes. So yeah, we have proved the first identity. Second is trivial. From here, what we do, I have said earlier that we since log of x is less than x, so we can absorb this by big O of x. And this is also a similar kind of calculation. So we get all this. So all these three, I mean, not all three, these two functions are averaged by this. Now we state one important theorem of Shapiro's theorem. So what he writes out that if we have a non-negative sequence of numbers an such that we can average this sum, this partial sum, by this for all x greater than or equal to 1, then we have this. That means we can delete x from here, from here, from here. If we have a non-negative sequence of numbers with this identity, then we can delete x from here, from here, from here. That's what this is saying, roughly saying this. Okay. So yes, now we can apply this here. Yeah, so we are not going to, I think, prove this. You can take this as an exercise, and you can see the proof of this theorem in any standard number theory book. So yeah, so we can use this theorem to get rid of x from here, from here. All right. Yeah. So if we choose our an as this log of n, if n equal to p, and if we can choose 0 otherwise, then we have this. Because from here, we have this hypothesis. So this is the hypothetical statement. We first have to, we need to have this. So if we choose a of n as log of p, so we know this is true. So then we apply this theorem here, then we get this bound. And you can see that from here also that the primes are infinite, because see here we have that that when x goes to infinity, log of x going to infinity. So this sum is also going to infinity. So from here we can also say that prime side. So here, so when you study number theory, you can see many proofs that asserts that prime side finite. So now we'll see one important object which is called Dirichlet characters. And the study of Dirichlet characters is very famous in number theory. We are just giving some preliminary ideas, but once you study deeper and deeper, you will get to know how these functions are involved in number theory. So, okay, let's just define what is this Dirichlet character. So, if G is a finite abelian group, then a complex valued function f, which is defined on this group G, is said to be multiplicative if f of AB is equal to f of A times f of B for all the elements A and B of G. And of course, as f has to be non-zero, that is f has some non-zero values. So in particular, if we choose G as this group, where this is the group of the reduced residue system modulo n. That is, it contains all the integers which is less than or equal to n and which are co-prime in simple language. Then corresponding to each character f of this group G, we define an arithmetical function which is denoted by chi as this. So if k and n are not co-prime, then we assume that this value is 0. If they are co-prime, then f of k will absorb this value f of k hat, where k hat, so this is the residue class which contains k, right? And this function is called the Dirichlet character modulo. Now we'll introduce one more interesting topic, which is known as Dirichlet L functions. So this function is defined like this. So if chi is a Dirichlet character and s is a complex variable where the real part of s is greater than 1, then we define this series. And it is easy to see that this this converges when the real part of s is greater than 1. And this series, of course, whenever we choose s is when a real part of s is greater than 1, so it behaves like a function because this will converge. So so this series is called the Dirichlet L function. One of the important theorem Dirichlet proof is that this Dirichlet function, when we evaluate it at s equal to 1, is non-zero when chi is not principal character. So not principal character means so principal character means that it takes values 1 whenever when the argument is co-prime to the modulo. If it's not co-prime, then it will take value 0. In fact, this the non-vanishing of this Dirichlet function when s is not a principal character, it is a consequence of, we can say that it appears in the proof of Dirichlet theorem. But this kind of problems where the vanishing and non-vanishing of this Dirichlet L functions are quite famous. I mean, or can say some hot topic nowadays. Now we recall some of the identities which involve the Dirichlet characters. So if chi is any non-principal character modulo k, and if x is greater than or equal to 1, then we have that this sum. If you consider this sum over all the integers which are less than or equal to x, then this partial sum is equal to this infinite sum, and then we go of 1. Similarly, we have that this partial sum can relate with this. The proof of this is not very difficult. I leave this as an exercise because you can have a nice proof of these two identities in any basic books of number theory. Here we omit these discussions because of lack of time and lack of space. So here we use this notation L prime of 1 chi for this function, for this infinite series. We'll fix this notation. So now we are at the final step to prove the Dirichlet theorem on arithmetic progression. So here we to prove this, we will prove a lot of lemmas. We can consider a lot of identities we need to prove, and once we prove all these identities, we'll get the Dirichlet theorem on arithmetic progression. So first, we have this. So first we have this. We have seen in our in one of our slides, we have encountered that this partial sum log of p over p, where this sums over all primes which are less than or equal to x. So this is log of x plus big O of 1. So this we have already proved. Next, we want to show that if we consider this reciprocal log of p over p, where the sum over all the primes which are less than or equal to x, and p is corresponding to 1 modulo k. So this partial sum we can express in terms of these three identities. So now if we can show that this identity, so this would be some big O of 1, then I think we are done. Because then this would be big O of 1, and it is big O of 1, and then log of x will be here. Then from here we can say that the primes are. So next we'll show that if chi is a non-principal Dirichlet character, then we'll show that this for any character non-principal character chi, so we can show that this sum is equal to this. And here we are done if we can show that this thing is equal to big O of 1, right? And this is what exactly we are doing in the next thing. So next we'll show that this sum, where this will exactly appear like this. So this is when multiplied by this L of 1 chi, so this would be big O of 1. Now from here, I think we can say that this is big O of, this would be big O of 1, then this would be big O of 1, so ultimately this would be big O of 1. If we can show that L of 1 chi is non-zero, then we can just take this here and then say that this would be big O. But if it is 0, then we cannot say. So the thing is, ultimately what we are having, that we can show that that if this is non-zero, then just repeat. Again, for example, suppose if this is 0, if L of 1 chi is 0, suppose, then we can again show that this would be equal to log of x plus big O of 1. And then ultimately, what we will show that this identity, when we consider h as 1, would be equal to this log of x plus big O of 1, where n of k is the number of non-principal characters chi modulo k such that L of 1 chi equals to 0. So if we can show that, that nk equal to 0, that is, there is no non-principal character chi for which L of 1 chi equals to 0, then this would be 0. And finally, this non-vanishing of this L function at as equal to 1. So here we'll first prove step 1. And to prove this identity, so I'll leave this as an exercise because you can have the proof of this in any standard theory. So the thing is, here we'll prove up to this. This I'll leave as an exercise because this is some simple manipulation. All right. So yeah, again, go back to this. Yeah. Can you see my slides? Oh, you can't. Sorry, how to get this full screen. Yes. Yeah. So yeah, so this is our lemma 1. So yes, for x is greater than 1, we have to show that this average of this would be equal to this. So here we recall this identity. So we have, so it is known to us that log of p over p, compute the sum, all the primes, where the sum varies over all the primes less than or equal to x, and this is equal to log of x plus big O of 1. So now we use one famous relation, which is known as the orthogonality relation of the Dirichlet characters, which gives that. So if we consider this sum, so where the sum runs over all the Dirichlet characters 1 to 5k. Yeah, it is one thing I forgot to mention that. So if we considering Dirichlet characters modulo k, then we have phi of k number of characters available for our group z by kz star. So these are the only Dirichlet characters, that is starting from 1 to up to 5k. So there are 5k number of Dirichlet characters every modulo k. Modulo is important. So yeah, so this is a famous relation. So this is known as the orthogonality. So if we apply this, what we have that if we consider the sum, where the sum runs over all the characters, then this would be equal to p of k if this m and n are equivalent to n. I mean, if m is equivalent to n modulo k, m is here and equal to 0 if m does not congruent to n modulo k. Okay, and you can see the proof easily. I mean, again, in some books, these are very basic, so you can you can find a proof of this identity anywhere. In fact, you can Google it. You can have a nice proof of this result. So using this orthogonality, so what we have that, so if we apply this orthogonality here, if we consider, if we multiply here by log of p by p and take the sum here like this is exactly what we are doing. So we are multiply here by log p by p and then sum it over all the primes which are less than or equal to x. Then we obtain that. So see here, so this sum depends on p and h. So see here, we can compute this over any pair of numbers m and n. So here we choose the pair as p and h, right? So we have that this sum is equal to p of k if p is equal to h congruent to k, otherwise 0. All right, so this sum will survive only for those primes for which p congruent to h modulo k. Otherwise, this sum would be 0. So yeah, we're getting exactly here. It's the same here. So we have here phi of k, and then we have log p by log p. So this will remain as constant. And yes, so we have all such pairs p congruent to h modulo. All right. So yeah, so from this we obtain that this phi of k times log of p by p, where the primes congruent to p modulo h modulo k, then the sum is here appear like this. So now what we will do here, we will take the principal character out and we take other sums are inside. So here we're doing that. So if we choose chi of 1 as the non-principal, as the principal character here, so choosing chi 1 as the principal character, we obtain that the sum is equal to this, right, plus this. So here you can note that that since I mean this h is co-prime, h and k are co-prime, right? So h and k are co-prime. So chi 1 of h is always 1. Similarly, so chi 1 bar of h. Yes, for chi 1 bar is the multiplicative inverse of the character chi 1. Similarly, here this chi r bar, so it denotes the multiplicative inverse of this character. And okay, so here we have the sum is remains like this, and then we have chi 1 of p log p by p, and the second sum will start from r equal to 2 to phi of k, and this will consider this as it. All right. Yeah. So here it is well known that chi 1 of h is equal to 1 because h is co-prime to k. And we have that chi 1 of p equal to 0 unless p and k are co-prime, in which case we have chi 1 of p equal to 1. So hence we have that. So here we will do exactly the same. So yes, so if we consider this sum log p by p, so this will be exactly equal to if we in the sum, if we consider all the primes which are less than or equal to x and which are co-prime to k, then here we consider all the primes and then we subtract those primes which are multiples of all the primes which divides, right? So here we have that this would be equal to log of p by p, where the sum over p, all the primes p less than or equal to x. And this is a finite sum because since k is a fixed positive integer, so all the prime divisors, I mean, there are finite number of prime divisors, so this sum is finite, so we can bound them by O of 1. So here we have this. So now I think it is straightforward by combining this 1, we have this 1, 1, then 2, and then 3. So we get the identity. So now we are going to prove lemma 2. So here what we are considering, similarly we are considering x greater than 1 and chi is a non-principal Dirichlet character. Then if we consider this sum, where the sum runs over all the primes less than or equal to x, then we'll show that this is equal to this plus big O of 1, where L1, L prime 1 chi is defined in our earlier slides. We have already defined this, and here mu is the Mobius function. So here we'll begin with the sum here. So what we do, we first begin the sum. It appears on the, we consider this sum where this chi of n is a Dirichlet character, and this Melgo function. So this is the lambda function which takes values log p if n equal to some p to the m and otherwise 0. We consider this sum here, right? So yes, if we consider this sum, then if we can see that this takes value 0 when n is not a prime power, right? So we can write this sum in terms of prime powers here. So here what we do, we consider all the primes which are less than or equal to x, and here we consider all these powers of p to the a, where this p to the a is less than or equal to x, and we consider this sum. So this is, and then we put this lambda of n, the value of lambda of n at p to the a. That's it. So we are doing like this. Then what we do here, we'll separate this case here. So first we consider a equal to 1 separately here. You can write like this, where a equal to 1, and for a equal to 2, we'll have this. So now note that the second sum here, so if we consider the second sum here, so what we obtain, so we can say that this in the second sum we have this chi of p to the a, and it is well known that the characters, the absolute value of a multiplicative character is 1, right? So we can say that this sum is majorized by this, like this. So here what we do, here we consider, in place of this, we take 1, and we can take log p out, and we consider this sum, where this is a geometric progression. So we know, so this is an, infinite geometric progression. So we know how to sum this. So we obtain this sum as like this, and clearly this is less than log of n, and then by n into n minus 1. This is trivial because here we consider all the n's, not the primes. And we know that this would be as the big O of 1 because log of n is less than n, so this would be big O of 1 simply. So that means this would be big O of 1. So we have now that this expression, this would be like this plus big O of 1. Now, also it is well known that this mango function is the uh, is the it can be written like this in this divisor sum, where the sum runs over all the divisors of n. Mu d is the Mobius function. So yeah, it is well known that this is equal to this. So then if we consider the sum here, so like here, let's choose this one here. So we replace this mango function by the sum, divisor sum. So here we have chi of n here, we have chi of n here, and here we have sum, which is the divisor sum here. And if n is c into d, that is, if we can write n as product of two numbers c and d, then we know that chi is multiplicative. So chi of c and d is equal to chi of c into chi of d. So we employ that here. So we take out all of these, all the functions which contain d here. So we choose d here like this, mu d, and then chi d and d here, and then we left with the c, which is less than equal to x by d, and then here we have x of c, because here we have x of d into x of c. So here we have chi of c into log of c, because we already take out d here. All right. So now since x by d is greater than or equal to 1, so therefore what we have here, so we can say that this sum, we consider this sum, so this sum is can be expressed like this. This we obtain in our formulas involving Dirichlet series, right? We obtain this. Hence, what we obtain here, if we use this identity here, what we obtain is, we obtain that chi of n times this mango function n by n. When we average this, we obtain that this would be equal to, I mean, we have this L prime of 1 chi, and then like this, and then like this. This is just simply substituting this here, and we obtain this. This is just simple substitution. And now we can say the term inside this big O. So yes, we can say that. So we can write this like this. All right. And we can say that this would be equal to the floor of x times log of x, because here d is running for all the integers which are less than or equal to x. So if we take the sum, then we have how many integers are here less than or equal to x, we have to count. So this is the exact count we have, right? And then minus of this, which is equal to big O of 1, because if we push x inside, then we obtain that this would be big O. So ultimately here we have this big O. Since we have that log of d, consider the sum d less than or equal to x, then this would be equal to log of x factorial, which is equal to x log of x plus big O of x. So if we put x inside here, we obtain that this would be big O. It is very trivial. So therefore, what we have that is the sum, we express this like this, the big O of 1. So finally, if we use this in our where we have here log of p here. Yes, yes. So yeah, after using this in our previous identities, we obtain. These are simply manipulation of all the calculations. They are not very difficult. So now we're going for our lemma tree. It gives that if x is greater than 1 and chi is non-trivial character, then we have that. Then this partial sum is equal to big O. From here, we can say that if we know that this is not 0, then this would be exactly equal to big O. And then we're not. So we are going to prove this. So it is well known that if alpha is completely multiplicative, then we have g of x is equal to like this, first the sum of alpha and f like this. Then we can write f like this. So this is kind of like, so this is called the Mobius inversion. So if we have g and something like this, we can get f. So now if we choose our completely multiplicative function alpha as chi, the character, if we choose f of x as x, then what we have here? Then x, in place of f of x, we can write x here. Then we have x would be equal to this identity, right? G of x by x. Where what is our g? So g is like this, right? And we have that we can take x outside and we consider this partial sum, chi of n by n. All right. And then again, if we use the properties of L function, then we can write the g of x like this. X times L of 1 chi plus big O. So that's what we have here, x from here. So we have x here like this. Where we replace g of x by n by this. Right? So now multiplying this, what we have is this. So here we can say that this is big O of x because here we have that in this sum, if we consider this sum here, so these are absolute values are 1, so these are bounded by x. So this sum is bounded by x. So we have this big O. So finally, if we divide all the terms by x, we obtain opposite. Next, we are going to prove that if chi is non-principal Dirichlet character, and if L of 1 chi equal to 0, if, which is eventually not true, but suppose if it is true, then we have that this L prime of 1 chi times this partial sum would be equal to log of x plus big O of 1. So here we again use the Mobius inversion formula, but for these two functions where we use f of x like x times log of x, then we obtain that x log of x equal to this, where alpha is again our type, the Dirichlet character type. So we have, so if we have like this, then g of x can be expressed like this. So here what we have is we can take out x log x, and then we can apply here the property of log of a by b equal to log of a minus log of b. So we apply that. Then if we use the property of L function, then we can replace this sum by L of 1 over chi, 1 comma chi, and big O of 1 over x. You can replace this by this, and we can replace this by L prime of 1 chi, right? And we have assumed that L of 1 chi is 0, so this will be 0, and we have left with x L prime of 1 chi plus big O of log of x, because here if we push x inside, we have it is bounded by big O of log of x, and here we have similarly it is bounded by this big O of log of x. So therefore, what we have here is if we replace g of x here, obtain that x log of x will be equal to this. So now simplifying this expression, we obtain this. So here also note that this mu of n and chi of n, so this absolute values of these two functions are 1. So here we can bound this by 1. So here we have chi of x minus log of x minus log of x. So what we have is that, so now we are having like this. So now we have to average this. Yeah, and it is easy to see that this sum would be big O of x, because here we have log of x is less than x, and similarly this would be less than x. Big O of x. So therefore here we have big O of x, and we have on the left side we have x log of x. So we have this identity. So once we cancel out x from this all this all this 3, we obtain this proves the lemma. So next part of the proof is to show that if we consider x greater than 1, and if we consider this partial sum of log of p by p, where the sum varies for all the primes for which p congruent to 1 modulo h. So here mind if we consider 1 in place of h. So I'll explain it later while I'm taking 1 in place of h. So suppose h equal to 1, then if we consider this partial sum of this function, then we obtain that this in terms of log of x plus big O, where this particular number nk, so this is the number of non-principal characters chi modulo k such that L of 1 chi equal to 0. And in fact, this will prove that this would be 0. So if it is 0, then we're done, because if it is 0, it is, if there is no non-principal character for which L of 1 chi equal to 0, then this would be 0. And then this is the exact expression we are looking for. So now, so what we have is, so if we use lemma 1, then for h equal to 1, we obtain, we just recall all our relations for in that appears in lemma 1, 2, and 3. So here, so if we use lemma 1 for h equal to 1, so we have this, we make it a star. And if we use lemma 2, then we obtain that this sum would be expressed this way. And if L of 1 comma chi-r is non-zero, then in lemma 3 we have shown that the right member of the star is 1. But if L of 1 comma chi are equal to 0, then we have shown in lemma 4 that this product with this would be equal to minus log of x. So therefore, using all these relations, we have this identity. So 1 over p of k and sum of all these characters starting from r equal to 2 to 5k, we consider the sum, where the sum runs over all the primes p less than or equal to x, we obtain that equal to like this. And if we substitute this identity in our star relation that is stated in 1, we obtain this. And this is exactly what we are looking for. So our next job is to show that n of k, n of nk is equal to 0. That is, there are no Dirichlet non-principal Dirichlet characters for which L of 1, 5 is equal to 0. That is, it is never vanishes. So I left this as an exercise when to show that n of k is equal to 0. So this you can see in any number theory book where you have where you can see that n of k equal to 0. So yes, so after getting all the calculations in this last lemma, lemma 5, I guess, yeah, lemma 5, if we combine all the lemmas 1, 2, 3, 4, see obtain like this. And since n of k equal to 0, so this would be equal to this. Okay, so that means if x goes to infinity, we have log of x going to infinity. So the left hand side is also going to infinity. So that means there are infinitely many primes which are congruent to 1 modulo k. All right. So yeah, so here the point of choosing 1 is that it is the thing is that we have seen earlier when I can show you here just a moment. Right, now is the Dirichlet. So where are Dirichlet? Yeah, so this is our ultimate goal to show. So here you can see that on the right hand side there is no term containing h. In particular, this is our main term, you can say. So in this term there is no term appearing in h. So that means this is independent of h. We can choose any h, 1 up to k minus 1, which are co-prime to k. So yeah, and also this gives this gives an idea that you can think that the primes then you can think that the primes in each of the reduced residue class modulo k are evenly distributed. So this is a distribution of primes. So this is a different area in number theory. You can pursue this as here as a topic of research. So yeah, this is the base. This is the base case. I mean, the primes are infinite, and how they are distributed in their residue classes. So we can say that since from here we have that this h appearing here is so there is no h appearing. So this identity is dependent on h. Whatever h we are choosing, which is co-prime to k, we get the same averaging formula here. So we can say that the primes in each arithmetic, the primes in an arithmetic progression for the primes and primes if in a reduced residue class modulo k, so they are evenly distributed. Okay. So that's all. So I left many results as an exercise. So I hope you all can can go through the proofs of those that I have left as an exercise. So yeah, so that's all. And thank you so much for listening. So if you have any doubts, any queries, please keep asking through email, through message, so whatever source you are having. So yeah, I hope you all are you all have enjoyed. So yeah, and thank you. Bye bye.